My Proxxon mill has built up a large amount of backlash on the x-axis in recent years. All in all, it's about 700 microns, which is way too much. The strange thing is that on the y-axis, there is less than 200 micron of backlash. In this video, I investigate the cause and solve the problem. Indeed, that's a horrible amount of slack. And what is striking is that there is a yellow glow over the most used part of the thread. You can see the worn material of the nut on the axle. There is virtually no yellow glow over the y-axis, and the nut for the x-axis seems to be made of different material than that of the y-axis. This last nut has approximately the same red-yellow color as that of my piece of bearing bronze, while that of the x-axis is really yellow. I'm starting to wonder if that worn nut is actually made of bronze. I'm going to do some hardness tests to try to find out if it could be a material other than bronze. The Vickers test is suitable for almost all materials. A pyramid-shaped diamond is pressed into the material with a precisely determined force, and the length of the diagonal then determines the hardness. This nut from Proxxon has a hardness of 137 Vickers, while that of my piece of bearing bronze just reaches 70. That does not provide any real certainty about the type of material, for which I would have to do an X-ray fluorescence measurement. But based on these measurements, I will certainly not rule out that the nut of the X-axis is in fact made of brass. Anyway, it's so terribly worn that I have to make a new one. But before I do that, I first want to check the M16 2mm pitch threaded rod itself for wear. And that doesn't look encouraging under the microscope. Some accurate measurements with a micrometer confirm my suspicion. The shaft also has its share of play, about 100 microns in the middle, virtually nothing at the unused ends. Indeed, the short Y-axis shows virtually no wear. I could purchase a new nut and axle, but of course, there is little objection to, say, an M15.82mm pitch axle with a suitable nut. So let's try that first. Oops, that's never going to fit. I will have to show some creativity to make cleaned up threads with this too short lathe. The first thing I need to do is extend the lead screw on one side. Then that extension can be clamped into a collet, allowing me to recut the thread all the way to the end of the lead screw. I clamp the axle nicely centered using an aluminium clamping sleeve. A 45-degree chamfer in the lead screw and a tightly screwed M8 bolt with the same chamfer should suffice. The lead screw will run pretty true after I machine the outside of the bolt. There is a keyway exactly where the steady rest should support the lead screw. A steel bushing that fits tightly around the axle solves this small problem. Off camera, I check the vertical position of the lead screw in the same way. When recutting the thread, it is important that the tool bit has the correct amount of clearance. The M16 thread requires an angle of at least 4.5 degrees, and with a minimum of 5.5 degrees clearance on the left side, I need a side relief of 10 degrees and a top angle of 60 degrees. For the front relief, I choose 8 degrees. I grind the radius of the tool bit tip for the bottom of the wire, manually using some small grinding stones. A follower rest must prevent the shaft from bending too much under the forces that arise during cutting. Two passes of less than 1/10 of a millimeter deep was sufficient to clean up the entire thread, and the result is a much neater thread, with the measured deviation reduced to just 1/100th of a millimeter. Now that the lead screw is fixed, it's time to make the nut. The problem with this is that there is very little room for a desirable larger nut. The dimensions of the old nut are about the maximum, although I can make the thread a little longer. I want to make an adjustable nut and am inspired by the well-known half nuts. The lower half is tightened against the table with two M6 bolts. Two flank couplings go over the same bolts and tighten the top half. The shafts of the flange couplings fit tightly into the holes in the bronze. After adjustment, the couplings are secured with an M3 set screw and a plastic plug. With my tabletop bandsaw, I cut out the rough shape of the nut, and with my mill, I cut it to size and square. This is so much better. Not only has the backlash been reduced to a few hundredths of a millimeter, the nut is now adjustable. And I suspect that the excessive wear from before, with this bearing bronze nut and smooth threading on the lead screw, has also disappeared. Okay, that's it for this time. Thanks for watching.